sample size is small.
Sample size is irrelevant.
How do you know the population, the actual population of the sample is unbiased? But how do you know that they're equal? Not a person, not whatever, but how do you know that it is all equal? So that you
Suppose you have a sample of size 1.
yeah, okay.
Suppose you have a sample of size 1. On average, what value do you expect to observe in that sample of size 1? The sample mean. I mean the population mean.
So if you took that one enough times, you would get the
Yeah.
and you average all of that and you get the
I know. If somebody asked you, I have a really great mind thing to do later on. I have a barrel. We're going to play this game again later on.
Barrel,
I have,
a billion balls.
there's too many to keep track of. Well, 8 balls, so there's 8 balls in the jar. But they're numbered at random. No, no two is the same number. So they're not. We have a barrel of numbered balls. There could be ping pong balls or something else. And there's a bunch of them in there. Nobody knows how many. And I'm willing to provide, you come to the castle. You've heard that the princess is looking for a husband. And you come to the castle. And you've heard that I'm a cranky old king. But nonetheless, you come to the castle and you've asked the king if you can have the princess's hand in marriage. And so I say to you, home, if you can guess
How many balls in the barrel?
no, we're going to come to that one later. If you can guess the average of the numbers on the balls, I will give you my daughter's hand in marriage, princess's hand in marriage. But if you don't get it right, I'm going to feed you to the lions. All right. And there are many balls in the urn. You couldn't count them fast enough to figure. Even if you were the Rain Man. Dustin Hoffman was an idiot savant, and the Rain Man could look at the toothpicks spilled on the ground and tell you how many there were. Right? Well, you're not the Rain Man. So that's the proposition. And I will let you pick 2 balls out of the urn. If you get the population mean right, you get the princess. If you get it wrong, it's your dog meat. So what are you going to use as your estimator?
The average of the thing that I picked because I had nothing else to go off of. Because it's unbiased.
Right. So it's unbiased. If you were allowed to do it over and over and over again, the mean of those samples of size 2 would tell you the truth. Suppose that I only let you pick 1 ball.
That would be it.
You would pick that number as your guess for the mean. Because if you know that you did it over and over and over and over and over and over again, and then average those guesses, that would equal the truth. So that's the notion of unbiasedness.
It's over.
Yeah. That's not a question of the sample size. That's the question about the replication of the experiment. Is everybody clear?
Guess I'm marrying your daughter.
So everybody clear on consistency?
We're clear on bias now.
But not, it's not,
Okay, so now you can epsilon as small as you want.
let's take this part away. You understand that part, right? So the index n on the theta hat tells me how big my sample size is in the construction of theta hat. So if n is 1, it's a sample of size 1. If n is 100, it's a sample of size 100. And the probability statement says the probability that theta hat sub n differs from theta by more than epsilon is equal to 0.25. So there are 2 things that are open questions. N and epsilon. And my argument to you is that if you pick epsilon, I can pick an n to make that probability statement true.
So what you pick, one of them, you're going to go.
Right. Okay. You guys have solved enough probability questions for these basic statistics to know that you could do that, no problem. So all I'm saying is that it's possible for you to pick epsilon really small, thinking that I'm never going to get that probability. I can't possibly figure out n. But I know that I can. So now, I ask you, what happens to that sequence of probabilities? So, really have some more board here. There's a PDF of the sample mean based on a sample of size 20. And we know that from the earlier discussion about unbiasedness, that the mean of that nice symmetric distribution is here. So when the sample is sized, and let's pick epsilon to be, so there's mu minus epsilon and mu plus epsilon. And so the probability that I differ from mu by more than epsilon when the sample is size 20 is that. And let's transfer everything down to the next line. Suppose that I increase my sample size to 100. What happens to S squared when I increase my sample size to 100? The sample variance. What happens to the sample variance when I increase the sample size to 100? It gets smaller, right? Because I got, instead of having 20 in the denominator, I have 99. And so the implication for my picture, if I can get it to look right. So now the probability that my sample mean differs from the population mean by more than epsilon is real small. And if I increase my sample size again to 1,000, I can put another panel underneath, and then the area on the tails gets really small. So what it's suggesting is that this notion of consistency is suggesting that the density is collapsing on the truth as the sample size gets larger. Yes?
Are there any limitations on what the random variable is? Like, you have a distribution that would not continue to discrete the random variable. Take one of 3 values, it would almost always say 1 value, and then could that affect this at all or no?
No.
Because you could the average to end up, say, especially if the sample size is small, so I don't know, 5 or something like that, and you have a whole bunch of things that would all have the same average, that all the same draw for all of them.
Well, let's consider a die. A 6-sided die numbered 1 through 6. 1 spot, 2 spots, 6 spots, all the way through. If I throw the die once, what's your best guess for the number of spots that are going to show?
Doesn't matter, it doesn't matter.
3.5. That's the expected value of the number of spots that will show. Because a number 1 shows a 1/6 of the time, the number 2 shows a 1/6 of the time, and the number 6 shows a 1/6 of the time. So your best guess for the number of spots it's going to show is 3.5, and it's an unbiased estimator.
Because it's a loaded die, it still wouldn't make any difference. It always...
You sure it would. If it's a loaded die, it means that one face comes up more often than it's supposed to.
Right.
So now your best estimator is not 3.5, but you got to do a little experiment with the die because you change the distribution when you loaded the die.
So it shouldn't make any difference then. Like if you ran it, if it wouldn't make any... Yeah, I guess I'm just trying to think about it in that.
No, the underlying distribution doesn't matter. The estimator is consistent. It's consistent. And there are many instances. Not all data has a nice normal distribution. Does that mean that the sample mean is not consistent? No.